Just we will wait for 2 more minutes. We'll see anybody else will join on.
Okay, ma'am.
I think most of the students might be busy due to net exam. It's on this Sunday or Saturday, right?
Sunday, ma'am.
Sunday. Yeah, I think maybe everybody is preparing for that. That's why today only very few number of people has joined. Okay. So anyway, I'll start my session. So today we will be learning about solid state. Whether the slides are visible.
Yes, ma'am.
Okay, fine. So today we will be learning some basics theories about solid state, and then we will move on to solving some questions. So I have chosen 4 questions from different GATE chemistry question paper. So in order to solve that, whatever theories we need, we will just look into that in initial few slides, and then we will move on solving questions. So the first thing we should know is what is a unit cell. A unit cell is the smallest repeating unit of a lattice from which an entire crystal can be built up. So if this is the cube, we have x, y and z axis, and A, B, C are the unit intercepts made on the unit plane ABC on the crystallographic axis x, y and z respectively. And alpha is the angle between BC, beta angle between AC, and gamma is the angle between A and B. So these 6 parameters A, B, C, alpha, beta, gamma. These 6 parameters are called as lattice parameters, and with the help of these 6 parameters we can define any unit cell, any crystal system. Okay, so now what are crystal systems? There are 7 different crystal systems starting from cubic, tetragonal, orthorhombic, monoclinic, hexagonal, trigonal, triclinic. And as we saw earlier, A, B, C and alpha, beta and gamma are the lattice parameters, and based on their relation, we can define what is a crystal system. For example, cubic is the most symmetrical system with all the lattice parameters A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degree. Whereas triclinic is the least unsymmetrical system with none of the parameters being equal to each other. Okay, so this table is very important. You can take a screenshot because some questions are directly asked from this table, giving the lattice parameters connection and to define what is the crystal system or which crystal system this one belongs to. So this table is important. Now, the seven crystal system I have shown this. This is how symmetrical it is, how it will look. Moving on to the next important thing is Bravais lattices. So there are four type of lattice majorly: primitive, body-centered, face-centered, and base-centered. We will learn about each lattice in the coming slide. Just we have to know that in each crystal system, for example, let us take cubic. In cubic crystal system, there are primitive, face-centered, and body-centered Bravais lattices. So similarly, we have to know how many Bravais lattices we have. Totally, we will have 14 Bravais lattices. And the four lattices, how we will explain each one can be seen in the coming slide. Simple cubic lattice. Simple cubic lattice means it has atoms present around all the 8 corners. Okay, so number of atoms per unit cell is an important concept because many of the questions will be asked based on this. So we should know how many how many motifs are present in each Bravais lattice or each lattice. First one, we will discuss the simple cubic lattice or primitive lattice in which atoms are present only at 8 corners. So each corner is actually shared with 7 other cubes, meaning each atom is shared among 8 cubes. So the contribution of one particular motif will be only 1 by 8. So since there are 8 atoms at 8 corners and each contribute 1 by 8, the total contribution will be 8 into 1 by 8 equal to 1, and therefore the number of atoms present in a simple cubic unit cell will be equal to 1. Next is body-centered cubic lattice. In this, atoms are present at 8 corners as well as at the center. Similar to simple cubic lattice, but one more will be present at the center. So in this case, the corner atom contribution will be the same, 1 by 8, and 8 atoms means totally 1. And in center means this entire atom is contributing totally towards this cube. So the contribution by atoms present at the body center will be equal to 1. Therefore, the number of atoms present in a BCC unit cell will be equal to 1 plus 1 equal to 2. And the next one is face-centered cubic lattice. In this case, atoms are present at all the corners and atoms are present at the faces, all faces. Okay. So imagine here also we have one cube. So one face is shared between 2. So the contribution per face will be 1 by 2. So atom we have seen 1 from all the 8 atoms, and at the face the contribution will be 1 by 2, and there are 6 faces. So contribution by 6 atoms present on the 6 faces will be 3, and therefore the total number of atoms present in an FCC unit cell will be 4. Similarly, n-centered cubic lattices means atoms present at 8 corners and 2 opposite faces. So this also can be calculated as we calculated above. Corners means 1, face center 1 by 2, 2 atom, opposite face means totally 1 by 2 plus 1 by 2 will be equal to 1, and therefore the number of atoms present in an centered unit cell will be equal to 2. Is it clear? Or should I explain it again? Hello, is it clear? You can even send a message. Yes, ma'am. Okay, fine. Okay, now we can move on to solving the question. Okay, this is a straightforward question. If we know the first table which I had shown, you will get the answer to this. They have given lattice parameters A not equal to B not equal to C and alpha equal to beta equal to gamma equal to 90 degree. The crystal system is. So if we know the first table, the answer will be quite easy. So this is the table that I had shown above. A not equal to B not equal to C, alpha equal to beta equal to gamma equal to 90 degree. This is orthorhombic. So such a question does not require any time. We can directly answer such a question and it saves time and it is an easy mark. So you should remember the table which I had shown earlier, and this will you will get this is asked as a 1 mark question, so you will get 1 mark very easily. Now moving on to the next question. The metal crystallizes in face-centered cubic lattice with a lattice parameter of 4.20 angstrom. The shortest atom to atom contact distance in the lattice is. So what we know here is we have a face-centered cubic lattice. Okay. And the lattice parameter means A. A is 4.20 angstrom. We should find the shortest distance between atom to atom contact. For example, we have two atoms. Okay, we need. So that means we have to find a relation between A and R. R is the radius. So if we find the distance between A and R, then 2R, because R here and R here, so 2R will give the shortest atom to atom contact distance in the lattice. Okay, so now this is an FCC lattice. Atoms are present at all the corners as well as on the face centers. Okay, so now let us consider a phase diagonal from A to C. And in phase diagonal, even though it is shown like a small sphere, it is like this. Okay, imagine it is, sorry, it is like this much big. 3 spheres are present, each spheres touching each other. Okay, now the phase diagonal is how much? From here, if we start, 1R is present and this big sphere, 2R, and this sphere, half R. So R plus 2R plus R, meaning 4R. The phase diagonal is 4R. Now we can consider this as a triangle ABC, and A is given as the lattice parameter. If AB is a cubic system, so BC is A, then what will be AC? AC will be A square plus A square root of, right? So it will be root 2A. So from this equation and this equation, we can find that 4R, we can find that 4R equal to root 2A. Okay, so now we have got the relation between R and A. With this relation, we can solve the question which has been shown above. Now, the question has been asked only for FCC, but I will explain the relation between A and R for simple cubic lattice, which is very easy. A equal to 2R, FCC, 4R is equal to root 2A as we saw earlier, and body-centered cubic lattice 4R will be equal to root 3A. So these three relations are important in order to solve any such question that we have discussed earlier. So moving on, this also you can derive in the same manner that we have shown earlier for the case of FCC. In the same manner, you can derive this using Pythagoras theorem. So it is very easy. Now you can try it as an exercise. If you didn't get, I can explain, or if you have any doubt, you can ask me right now also. I'll explain to you, but this one is easy. So you try it once. It's similar to what we solved earlier in the case of FCC. Okay. So moving on to solving this, we found the relation for FCC to be 4R is equal to root 2A. And in the question, A is given as 4.20 Armstrong. So this is a straightforward equation. We can get from here R equal to root 2 into 4.20 divided by 4. R equal to 1.485 Armstrong. So in the question, the shortest atom to atom contact distance in the lattice is asked. So what is that? We discussed earlier, shortest distance will be R plus R will be 2R. Okay. So we have to just multiply this value with 2. So we will get the answer as 2.97 Armstrong. So the answer for the question, face-centered cubic lattice, lattice parameter 4.20, the shortest atom to atom contact distance will be 2.97 Armstrong. Is this question clear? Whether that question was clear, should I again explain? I hope it is clear. If you have any doubt, you can ask me now itself. Clear, ma'am. Okay, fine. Then it's fine. If you have any doubt in how we are deriving or anything, you can ask. If it is clear, then we can go on solving the next question. This question was asked in GATE Chemistry 2016, question number 8. When crystals of sodium chloride are heated in the presence of sodium vapor, they turn yellow. This is due to the formation of. So, 4 options are given: Schottky defects, Sprengel defects, F centers, and H centers. We have to find out what will happen when sodium chloride are heated in the presence of sodium vapor. How it is happening, why it is turning yellow color. So in order to know that, we have to go or understand a little bit of theory, or what is a defect. Defect can be of different types: line defect, point defect, or plane defects. So point defects are those in which there is a arrangement problem only at a particular lattice points or few points in a lattice or in a crystal system given. So, for example, like in a crystal, we have a perfect regularity in the arrangement of particles. So, any departure from such an arrangement can be called as a crystal defect or imperfection. And the major 3 classes of defects are line defect, point defect, and plane defect. In point defect, which is also called as zero-dimensional defect, from ideal arrangement, there will be only a limited region or a few lattice points which will be missing or dislocated, or extra atoms will be present. And this imperfection is caused in the case of point defects. Okay. Whereas in case of line defects, a linear disturbance to the periodic arrangement of the structural entities happens in the case of line defect, such as an imperfection arises in a particular row or column of a crystal during its crystal growth. Now, the plane defect means entire plane is having a disruption of the periodic arrangement of lattice points. This can be called as a plane defect or a surface defect. So the main important one is point defect. So the major questions will be asked from point defects. Line defects and plane defects are not that important. And the point defects can further be classified into stoichiometric and non-stoichiometric defect. In stoichiometry means the stoichiometry of a particular crystal, for example, NaCl or ZnO, remains the same. Whereas in non-stoichiometric case, in NaCl, maybe there can be an excess of metal or a deficiency of metal, which will cause a deviation. For example, NaCl there can be an excess of a little excess, means it is not in a proper stoichiometric ratio 1:1. A little excess is there or little deficiency can be there, which will cause a non-stoichiometry for the crystal, and this is a second category of the point defect. So among the stoichiometric defect, there are two major types of defect: Schottky defect and Frenkel defect. Many times questions are asked from these two defects. They'll give some general statement and will ask that whether these statements are correct or not, or this statement follows which defect, Schottky defect or Frenkel defect, like that. So knowing about these two defects are very important. Stoichiometric defects are of two types, Schottky and Frenkel. In Schottky, there is a missing of cation-anion pairs. Whereas in Frenkel defects, there is a shift from ion from its lattice space to interstitial points. For example, we have, these are the lattice space. Okay, for example, I am telling. Now, there can be a missing of one cation-anion pairs, which will cause a Schottky defect. But if this ion come from this lattice position and sit in the interstitial position, this will cause a Frenkel defect. In both the cases, the stoichiometry is not affected, because in this case, if cation is missing, anion is also missing. So stoichiometry is not affected. In this case, there is a mere shifting of ions. So in this case also, stoichiometry is not affected, neither the electrical neutrality. But since here there is a missing of cation-anion pairs, it will decrease the overall density. So the question can be asked like, a crystal undergo a crystal had some effect and the density has been decreased. So which among the following defect has happened? So you can tell it is Schottky defect, because in Frenkel defect the density is not decreased because there is no missing, there is just a misplacement of the ions. And in Schottky defect, the cation and anion have comparable sizes, whereas ionic crystals with cation size much smaller than anion will undergo Frenkel defect. Now, moving on to non-stoichiometric defect. Non-stoichiometric defect can be of three types: metal excess defect, metal deficiency defect, and impurity defect. In metal excess defect, there is a little excess of metal, like if the stoichiometry should be ZnO, but since it is 1 plus delta, this means that there is a little bit of excess of metal. So how can there be metal excess? Two possibilities are there. Either extra cations are present at the interstitial position, or anions has been missing. So if anions has been missing, means the metal is excess, or if metal is excess, like two cases are there. So the examples of both the cases are extra interstitial cation for ZnO and anion vacancies for NaCl. So in the question, it is asked about NaCl. We will explain that NaCl in detail later, but we are just explaining the main category now. Okay, so now we know what is a metal excess defect. Similarly, metal deficiency defect. In this case, cation vacancies causes metal deficiency defect, and the stoichiometry changes from Fe1O1 to Fe1 minus delta. So in this case, the other possibilities like extra anions in the interstitial position is not possible, because anions are generally bigger in size and this will not fit into the interstitial position. So metal deficiency defects can only be happen due to cation vacancy. And the third category is impurity defect. In impurity defect, as the name suggests, it is an extrinsic defect. An extra atom is coming from outside. For example, if we have a crystal of AgCl, and in this case, if two Ag plus are missing, one cadmium is doped into it, because Cd is Cd2 plus. So instead of 2 Ag plus, one Cd2 plus will replace, and the electrical neutrality is maintained, but there is an addition of a foreign atom or extrinsic effect. Impurity is present. So in such cases, we will call this as impurity defect. Okay, now we know about defects, how defects can be caused, what are the different types of defects that are possible. Now moving on to the main question that has been asked, that is about NaCl. So in the question, it is told that NaCl has been heated in the presence of sodium vapor. So we saw earlier, this is a metal excess defect due to anion vacancy. Metal excess defect will give a formula of Na1 plus delta plus and Cl minus. Okay. So how this is happening? When a NaCl crystal is heated in sodium vapor, it acquires a yellow color. Okay, this yellow color is formed because of F centers. How F centers is formed? When this is heated, sodium atoms will get associated with the lattice site and settle in normal cation site. Now we have extra cations, or that means we have an equivalent number of anion vacancy. So this is due to anion vacancy. And now if we don't have anion, we need to maintain the electrical neutrality, right? So sodium will convert to Na plus and electron. This electron occupies the anion vacancy. We can make understand better with this picture. We have metal anion, metal anion. So in one place, if anion is missing, this electron that has been obtained from Na converting to Na plus and electron will situate in this and maintain the electrical neutrality. Okay. So now this free electron can absorb light, and this is the reason for imparting yellow color to NaCl. And such an electron which is trapped in a particular lattice site is called as F center. And this F center, where F comes from the German word called Farbe, which means color. So this F center causes the color in NaCl, yellow color in NaCl, because such an electron has a delocalized nature and can undergo transition to a higher level by absorbing visible light, thereby giving color to a non-stoichiometric compound. So if in NaCl it is yellow, in other crystals like KCl, it will be violet, and KBr, it will be blue-gray. So the color produced by the F centers will be always the characteristic of the host crystal. Okay. So, and also in such crystal, due to the presence of free electrons, we can tell that these act as N-type semiconductors. Okay. So the answer to the question, when crystals of sodium chloride are heated in the presence of sodium vapor, they turn yellow, and this is due to the formation of F centers. Okay. Now, if it is clear, if it is not clear, you can stop me in between. Okay. So if you don't ask me, I will assume that it's clear for you. So if you have doubt, you can ask me, or otherwise I'll move on to solving the next question. This question was asked in GATE Chemistry 2017, question number 15. So P, F, and I represent primitive, face-centered, and body-centered lattices respectively. The lattice types of NaCl and cesium chloride respectively are. So we learned earlier what is P, F, I, etc. Right? What is primitive, face-centered, and body-centered lattices. Now the question is to find the lattice type of NaCl and cesium chloride. Let us freshen up our memory. Primitive lattice means motifs are only present at the corners. All crystal system has primitive unit cell. Body-centered lattice means motifs present at the corners and its center. Face-centered lattice at the corners and the center of face. And base-centered have all the corners and at the center of two opposing face. So in order to solve this question, one important concept we should know is about voids. Voids can be created in crystal. And there are various types of voids present. Okay. Tetrahedral void means the two important among one are tetrahedral and octahedral voids. Tetrahedral void means there will be four spheres, and in between four spheres there is a vacancy or void present. So that is called as a tetrahedral void. And if a void is present in between six six motifs, it is called as an octahedral void. So if we have a crystal with n number of atom in the crystal, then there will be n number of octahedral void and 2n number of tetrahedral void. So that like the typical definition, we can tell it as the interstitial space that gets trapped in between the spheres. Okay, the interstitial space that get trapped in between the spheres are called as voids or holes. So tetrahedral voids, generally we will, like, if we have 1, 2, 3, 4. 4, imagine the fourth one is above. So in between this we have a small gap, right? So this is called as a tetrahedral void. Similarly, if we have 3 below and we have 3 above, and this 6 comes in contact with a small gap in between. So this becomes an octahedral void. Okay. The vector space between 6 spheres is an octahedral void and 4 spheres is a tetrahedral void. Now, a next important concept is regarding this table in order to identify any structure. This table based on the limiting radius ratio, which is called as the radius of the cation divided by the radius of anion. That means radius ratio equal to radius of cation divided by radius of anion. Okay, so if a cation is larger, the larger will be the radius ratio. So that means the number of anions surrounding the cation will be larger, and that means coordination number is higher. What is coordination number? The number of anions surrounding a cation or a cation surrounding an anion. So if the size of cation is more, the number of anions surrounding it will be more. That means the coordination number will be more. So we can see that as the radius ratio increasing downwards, coordination number are increasing. Structural arrangement also increases from trigonal, planar to cubic. And examples we can see B2O3, ZNS, CDS, KCl, etc. So the structure asked to us is NaCl and cesium chloride. Okay, so we can move on to solving the question. But in many questions, limiting radius ratio will be given, like for example, ratio will be given as 0.226. So, and will ask what is the structural arrangement. So this will come in this category, and the coordination number will be 4, and structural arrangement will be tetrahedral. And examples are ZNS and CDS. So I will be explaining about NaCl and cesium chloride completely in this question, so that apart from asking directly the lattices of NaCl or cesium chloride, if they ask any other question related to such question, you guys will be able to answer that question. Okay, so we will carry out all the possible other questions that might be asked in such a question related to NaCl or cesium chloride. Okay, so NaCl is having an FCC lattice, which is represented as F, and the radius ratio of NaCl is 0.54, and it has an octahedral arrangement, as we saw earlier. Okay, it may be regarded that Cn minus has an FCC structure and Na plus occupies all the octahedral voids. Okay, so for example, if n number of Cl minus are present, we saw that there will be n number of octahedral voids. So the number of Na plus and Cl minus will be same in a crystal lattice. That's why the formula is Na1Cl1, 1 NaCl. Okay, so what we saw till now, there is one octahedral void per motif in a closed packed structure, and Na plus ion occupy all octahedral void. Okay. Now, we saw that it is having an octahedral arrangement, right? That means around each cation there are 6 anions. So presence of octahedral voids itself indicate that around it there are 6 motifs. So around 1 Na plus, there are 6 Cl minus, and around 1 Cl minus, there are 6 Na plus. So the coordination number of Na plus is to Cl minus will be 6 is to 6. This structure is also told to be an interpenetration of two FCC lattice, one of Na plus and the other of Cl minus, because this, when the arrangement comes into complete picture, where Cl minus adopt FCC structure and Na plus occupies the octahedral voids, this looks like as if two FCC lattice are interpenetrating to each other. So if an option comes like interpenetration of two FCC lattice, you have to go for this. Otherwise, you can directly select the FCC option. Okay. Now, we know we have calculated earlier the number of atoms present in an FCC unit cell is 4. So there are 4 Na plus, 4 Cl minus, because in FCC lattice Cl minus adopts an FCC arrangement. So there are 4 Cl minus present, and there will be 4 octahedral voids. 4 octahedral voids means 4 Na plus, since Na plus occupies all the octahedral voids. Therefore, the formula unit is 4 NaCl. Okay. And other crystals which have the same crystal structure are, examples are alkali halides except those of cesium, then NaBr, KCl, and oxides and sulfides of the alkaline earth metals, magnesium, calcium, strontium, and bromium, and silver halides except EgF, all have this structure, FCC structure, similar to NaCl. Okay. Now, cesium chloride. Cesium chloride have a simple cubic structure which is primitive, okay, which is represented as P. In this case, radius ratio is 0.943 and suggests a cubic arrangement. That means Cl minus adopt a simple cubic arrangement, meaning it will be present at all the corners of the cube. And cesium plus occupies position at the center of the body of Cl minus. There will be a cubic void created within the like Cl minus. For example, we have a cube and Cl minus adopt. Cl minus are present at all the corners, and there will be a cubical void present at the center, and Cl minus will be, cesium plus will be present at the cubical void. Okay. So this can be told to be a pseudo body-centered cubic arrangement. This might feel like pseudo body-centered cubic arrangement, but this is not. These are the only lattice point, and this is a void in which cesium plus is present. Now, as we can see here, one cesium plus is surrounded by 1, 2, 3, 4, 5, 6, 7, 8, 8 Cl minus, and if we extend this structure, we can see it is the other way also. So the coordination is 8 is to 8. This can also be found out from the earlier table that we have seen. If the radius ratio is 0.943, it has a cubic arrangement and the possible coordination is 8. And the number of atoms present in a simple cubic cell is 1. Therefore, the formula unit is 1. So we have calculated earlier how this is, because the contribution will be 1 by 8. 8 meaning 8 into 8 corners, meaning 8 into 1 by 8. 1. So 1 Cl minus present, and in between 1 cesium plus is present. Therefore, the formula unit will be 1 cesium chloride. And the other examples of crystal system which follow this particular structure are cesium bromide, thallium chloride, etc. So the answer to the question, the lattice types of NaCl and cesium chloride respectively are. So NaCl, we have seen that it is face-centered, and cesium chloride, we have seen that it is primitive. So the answer is clear. Do you have any doubt? Okay, fine. So, okay, clear. Okay, fine, fine. There are some more important structures like woodside structure and calcium fluoride structure, titanium dioxide. Question has I didn't find questions that has been asked in the gate, but it might be asked. So it will be better if you know such kind of structures also. I will tell you which are the important structures. Titanium oxide, or which is also called as rutile structure, sodium monoxide, Na2O, antifluoride structure, and huh, calcium fluoride. Calcium fluoride, which is fluoride structure. So these three are also very important. This can be asked. So check on the structure of this, and if you have any doubt, you can come and ask to me, or you can mail to me. I will be happy to help with you. And I think one more important equation, even though it is not related to question I am solving, one more important equation is related to the density. D is equal to Zm divided by Na into A cube. Questions have been asked with the help of this equation, where D is the density of a crystal, Z is the number of atoms present, like for FCC it is 4, BCC it is 2, and simple cubic structure it is 1. So Z is that, and M is molecular mass, Na is Avogadro number, and A is edge length. So using this, we can calculate the density of a particular crystal that is given. So this is also an important equation. So you should know that, and this might help you in solving many questions that has been asked in many competitive exams. Okay. So, and one more important concept that I would like to say is regarding X-ray. X-ray people, obviously, other questions will be taken, but this is an important equation that you should know in the case of X-ray diffraction. And one more thing is regarding powder diffraction pattern. One simple thing you should know is, okay, I'll tell you. There are HKL values. What is HKL are Miller indices. Okay. Based on Miller indices, we can find out whether a particular powder X-ray diffraction is allowed or not. So you should just see, this is a shortcut. So just you should remember this much thing. For simple cubic, all HKL values are allowed. Like if a powder X-ray pattern is given and in this all HKL values are given, that means the crystal structure is a simple cubic. Lattice is a simple cubic. And if only H plus K plus L is equal to even is given, then it is BCC. And if all HKL are either even or all HKL are odd, then it should be FCC. So these are some important things that you should know. Anyway, I am not going to solve any question related to that. That will be taken up. I don't think powder X-ray question has been asked, but regarding single crystal XRD using the previous equation, questions has been asked, and this is very important. So you should know this many things, and I think almost all solid state we have covered up here with that, and no more outside from this, nothing else will be asked from solid state. Almost we have covered up everything from solid state in this particular session. I have covered almost the theories or basics of solid state and answered some 4 questions. So all the questions are similar to this, or apart some X-ray diffraction questions are also there. This which is also pretty simple or pretty direct. Using the formula n lambda equal to 2d sine theta, we can get the answers. And if you find out any other solid state questions, you can ask me, mail me, I'll be happy to answer. So all the questions are clear. or should I explain something else? Is there anything else you want me to explain regarding this solid state? Then I'll be happy to explain. Is it clear? Okay, then it's good. Now, one more thing I wanted to show you is regarding spinals. Yeah, I don't think I have PPT here. Next class, I'll be teaching about spinals. So, what is a inverse spinal? What is a normal spinal, mixed spinal? So, regarding spinals, also every year questions are there, and if we know some basic things regarding spinals, we can easily calculate that, and it's simple calculation, and from that calculation, we can find out what is a spine, what is the spinal given in the question. So next class I'll be probably taking about spinals or about bioinorganic chemistry, either of these two. So if you should if you join next class, either of these two topics will be taken in the next class. And I think maybe today we have only very few numbers because of the net exam. So whether have you prepared for your net exam? Are you writing? Okay, it's good. Okay. I hope this also will help because solid state normally they'll ask pretty straightforward questions from solid state, and whichever topic I have taken, 18 electron or Waits rule, the tables and all are there. No, you just you might have taken screenshot, I hope. So that from that itself, just you give a glance to it, and with that you can solve most of the questions related to this. And solid state also, I hope you will remember for the coming exam, and you'll be able to answer all the questions. And while you are reading, if you have any doubt, you can ask me. Okay. Okay. Then I think I have almost covered every topic. Now I don't think anything is left. Oh, one more thing is regarding band theory. Band theory also come under solid state. So in band theory, it is pretty simple, and normally questions won't be asked. Matlab, not very difficult questions will be asked from band theory. Normally what conductor, insulator, from that they will give bands, like in a conductor valence band and conduction band overlap, and in semiconductor there will be an energy gap which is a small, and insulator energy gap is large. So I have seen question where they have given directly the band, and from which we have to find out which one belongs to which. And extrinsic semiconductors and intrinsic semiconductors. So extrinsic semiconductors means they are N type and P type. If there are extra electrons, as we saw in the case of defect, when there were extra electrons present, we told it as N type semiconductor. And if we have extra holes present, it is P type semiconductors, which can be obtained by a donor impurity. Okay. So these are the important things coming from like band theory. So in there will be a donor level in case of N-type semiconductor, and there will be a acceptor level in case of P-type semiconductor. And in N-type semiconductor, excess of electrons are the cause, and in P-type semiconductor, excess of holes. Okay? Only this many things are there. So I think nothing else state chemistry. So it is done almost. So I think you will be able to answer the questions. Now, if so, I think that now we can close the session if the questions are clear, or else I can explain it to you again. Otherwise, solid state chemistry, we have almost covered all the basics from the solid state chemistry, which is required to answer the questions. Like not a theoretical question, but calculation point of view. We have answered almost, but try to learn other structure which I have told you, like rutile, antifluoride, fluoride, and all. Questions might be asking from that also. Otherwise, calculation, all this number of atoms, A and R relation, density relation, all these are necessary, and Miller indices also. You just check on Miller indices, except that it is nothing else will be asked. Okay, so if it is clear, I'll stop the session, or if you want to ask any question, you can ask. Okay. Okay, then if there is no question, we can leave. Thank you. Thank you for joining the session. We'll meet at the next class. Thank you. Thank you, dear.